Okay, it's now time to prove the fundamental theorem of calculus, part 1. So fundamental theorem of calculus, part 1, states that you've got some big f of x, which is defined as the integral from a, some constant a to x, with some little function, f of u du, then the derivative of this function, big f of x, is actually just the little function evaluated at x. Okay, so there's a few things we're going to need to do this. And we'll state them as we need them. But first, we need to say, well, what is this derivative really? How do we define a derivative? Well, it's derivative, so d dx of f of x will also be the limit as h approaches 0. And let's go up and let's say we're defining f of x to be this integral. So let's use this integral in our limit definition of the derivative. So it's going to be the limit of the integral from a to x plus h f of u du minus integral from a to x f of u du all over h. Sorry about that. There we go. So we've got this guy. But we can rewrite it. Okay. There we go. I got it. Okay, so we can rewrite this guy. So it's the limit as h approaches 0 of, well, let's move this h down here to the front. So I've got 1 over h. And I'm going to have, this will be the integral from a to x plus h f of u du again. But this guy up here, I want to flip it around. So I'm going to turn this minus to a plus, and instead of going from a to x, I'm going to go from x to a. Alright. And you notice, well, hey, these are integrals of the same thing. One goes from a to x plus h, one goes from x to a. Well, hey, we can actually combine these. So this is the limit as h approaches 0, 1 over h, of the integral from x to x plus h of f of u du. Okay. So now this is what we're looking at. This is our derivative. But we need to figure out how to show that this guy is actually equal to just f of x, little f of x. So we have to do some in-between steps. So first, we're going to use the extreme value theorem. It says that extreme value theorem is going to tell us that there is a minimum and maximum value such that f of x naught and equals, let's have lowercase m be our minimum, and f of, let's say, x1 is our uppercase maximum. So this is our minimum, this is our maximum, with x0 and x1 are in our interval, and we need to choose what interval we're in. So this is true for any closed interval with closed ends. But we're going to pick x to x plus h, since that's what we're integrating over. And what it says is, well, here's my minimum value. There's a point which actually achieves this minimum value in here. So the point which achieves this maximum value in here. And what we're going to say is we've got this lowercase f of x is always smaller than our maximum and always bigger than our minimum for x inside our interval. Okay. Well, what good does that do us? Well, if we've got this set of inequalities, we can actually make this statement that the integral from x to x plus h of lowercase m du, du, so is less than or equal to, okay, I made a mistake. This x here, this guy should be u. This should be u is in here, because we're already using x as this variable. We don't want to double use x. So u is in this interval, u is in this interval, we're using f of u. Alright, so now when we integrate from x to x plus h, so we just f of u du less than or equal to the integral from x to x plus h of capital M du. Okay. Paper. So this gives us well, we can take this integral, so it's a constant, lowercase m. This will be mu evaluated from x to x plus h. This is going to be, well, this is an integral we're still trying to figure out what this guy is. Du. This guy over here will be mu, capital MU, evaluated from x to x plus h. And so we see we're going to get mx plus mh minus mx less than or equal to our integral mx plus mh minus mx. So we get some cancellation here, which leaves me with lowercase mh is less than or equal to my integral from x to x plus h of f of u du, which is less than or equal to capital MH. Well, I can divide everything by h now, which leaves me with my minimum value is less than or equal to 1 over h times the integral from x to x plus h f of u du, which is less than or equal to, okay. So what does this give us? Well, this gives us, here, this is our, if you remember, this is, as soon as we take the limit as h approaches 0, this is our derivative. So we've now got our derivative stands between our minimum value and our maximum value of this little function on x plus h. So we had to use the extreme value theorem to get that. Now we're going to have to call on the intermediate value theorem. So so intermediate value theorem applied to f of u, little f of u, is going to tell us that any value between little m and big M is in fact achieved for some u on our interval. Okay. And then, so specifically, So this tells us, so by the intermediate value theorem, there is, I'm going to steal the notation from the book, there is a C sub h. So there's some value between m, or no, excuse me. There's a C sub h contained in our interval in question from x to x plus h, such that if I evaluate little f at this ch, then it will give me exactly this value that happens to be between my minimum and maximum values. So h integral from x to x plus h, f of u du. So what just happened? Well, here's what just happened. So I know my function f of u is sandwiched between little m and big M. I also know that this integral, this 1 over h times this integral, is between little m and big M. So this is some value. I don't know what value this is, but I pick an x, I pick an h, there is a value for this. Okay. Now I come down here and I say, well, this value is in between these two numbers. Intermediate value theorem tells me, since I know little f achieves both of these values somewhere in this interval, that tells me there's another place somewhere in this interval where little f achieves any number in between m and little m and big M, specifically this number in between little m and big M. So I've chosen a specific element out of this interval that gives me this when I've got f of ch. Okay. But since c sub h is in this interval, we must have that the limit as h approaches 0 of the value ch must be approaching x. So we see ch is in this interval. As h gets smaller and smaller and goes towards 0, well, now I'm condensing this interval down to x. Well, the only place that ch could be is x as soon as I condense it all the way down. Right? Now, since f of x is f of u, we want to keep our variables straight. F of u is continuous. This tells me that the limit as h approaches 0 of f of ch must be equal to f of the limit as h approaches 0 of ch, which is equal to f of x. Okay. So this seems like it might be obvious, but it's actually not necessarily. Just know that it's true that if you have a continuous function, which are nice functions, we like them, most functions we have are continuous. Little f happens to be continuous. If you have a continuous function, and you've got a limit on the outside and something on the inside that goes to some value, you can take this limit and you can stick it inside the function. You're allowed to do that. If your function is not continuous, you might not be able to do that. But as long as we're continuous, we can do that. In which case, so this limit equals f of x. But even better, this limit happened to be So this limit as h approaches 0, so we've got f of x happens to be equal to this limit as h approaches 0 of f of ch, which is actually the limit as h approaches 0 of 1 over h. So recall, I chose my ch's, so f of ch is equal to 1 over h times the integral from x to x plus h of f of u du. But this guy, well, that's just the derivative of f of x, big F. So here's derivative of big F of x. Following this set of equalities gets me all the way to the fact that it is little f of x. So the key points in this argument are using the intermediate value theorem and the extreme value theorem. If you can understand both of those parts of this proof, then you should be good for the midterm.